Hello, everybody. In this video, I'm going to go through lesson 3.4, two-column proofs, and I want to apologize for the slight delay on this video. Oh, okay. Not what I meant to write. All right, two-column proofs. So this really is just going to be an example video, and I'm going to work through some examples. Proofs are something that takes a little bit of piecing it together, and it takes practice. So we're going to just look at some examples together. So let's start with example 1. And we have given CD, segment CD, is a median of triangle ABC. So that is our given. Segment CD is a median of triangle ABC. We are going to prove that segment AD is congruent to segment BD. And I will draw our triangle here, and you will draw this as well in your notes. So our triangle, let's see if it's going to autocorrect for me. That'd be so nice. So this is triangle A, B, C, and a median starts at one vertex and goes across and cuts the opposite side in half. I can do better. Let's see. See if I can move this little line. Oh, maybe not. Okay. Good enough. That is our median. And that is segment CD right there. All right. So we are going to start our proof. So a two-column proof has two columns. And I'm going to actually change colors. You have your statement column. And your reason. Come on, do the thing. There we go. Statement and your reason. All right. So the first thing you should always start with in a proof, no matter what, is what you are given. So our first statement, statement number 1, CD, segment CD is a median of triangle ABC. So segment CD is a median, and that is given. And that is our first step in this proof. All right. Now we kind of need to do a little bit more. So we know that this segment, and let's kind of look at this triangle for a second. Segment CD is a median. And as I said, a median really divides or bisects the opposite side. So it starts at vertex C and it bisects this opposite side, and the entire opposite side is side AB. So next, I would say, because this is a median, using the definition of a median, I'm going to say that segment CD bisects that entire segment AB, right? It really just divides it in half. And that is because a median of a triangle bisects the side opposite the vertex it's drawn. So sometimes your reason is a little lengthy, and that's okay. Sometimes you kind of have to explain yourself, and that's what we're doing here in a proof. So CD, this segment CD, it is bisecting segment AB because that's what it does. That's what a median of a triangle does, is it bisects that opposite side from which it's drawn. Okay, so now that we know it's bisected, looking back at what our goal is of this proof, our goal is to prove that AD, segment AD, is congruent to segment BD. Well, we know that this median is bisecting this side, so AD is congruent to DB. That is what happens when something is bisected. So now I would say this is our final step. Oh, I forgot to remember this is step 2. And step 3 is to say that segment AD is in fact congruent to segment DB. And that's just because a segment bisector, like that median, divides segment into 2 congruent parts. So if we have a segment bisector, it's bisecting some other segment, it is now being divided into 2 congruent parts. I'm just referring back to the definition of a bisector. So this is proven. Given CD is a median of triangle ABC, AD is congruent to BD. Okay, let's look at example 2. So this one actually started with one of my classes, and I just was not thinking that morning. So I definitely wanted to include it in this video. So given segment AC is congruent to segment BD, this is something different now. I'm going to draw a new figure. We are going to prove that AB is congruent, segment AB is congruent to segment CD. And our drawing here, we have a line segment. And this is A, and this is D. So the entire thing is segment AD, and then we have segment AC, which is congruent to segment BD. So looking at this here, AC and BD are 2 congruent segments. That is what we know. So I am going to start our proof. I have our statement and our reason. Oh, so much better this time. I think the key is confidence. Just gotta be confident with it. All right. So I always want to start with what we are given. Always start with what you know. So we have given segment AC is congruent to segment BD. So now that we know that, where can we go from here? And it's actually very interesting what we can do. So I notice that I have kind of the left segment and the right segment. They both share this middle part, this segment BC. And interestingly, BC is congruent to itself. So I'm going to say that segment BC is congruent to, and I'm going to spice it up. I'm going to say segment CB. I could say segment BC. It's the same thing. Just say it's congruent to itself. And that's because of the reflexive property. Any object, any number is equal to itself. So if I have this left segment and this right segment that are congruent, and they both share this same congruent piece, I could take that congruent piece away from these 2 already congruent parts, and I'd be left with pieces that are in fact the same. So if I have two congruent parts to begin with and I subtract away the same congruent piece, I will be left with two congruent segments. It's kind of just using the opposite of our segment congruence postulate as well as the segment addition postulate, kind of the opposite of the segment addition postulate. So I'm going to finally say here, I now know that segment AB and segment CD, those leftover pieces are congruent. So segment AB is congruent to segment CD. And that's really just because congruent segments subtracted from congruent segments are congruent. Or, I might say form, I like that better, form congruent segments. Okay. So that's proven. We did it. Given AC is congruent to BD, then AB is congruent to CD. All right, let's look at example 3. This one I think is my personal favorite. So it is given that segment CD is an altitude. I don't know, I said that kind of weird. Altitude of triangle ABC. We want to prove that triangle ACD is a right triangle. And I have our drawing. So let's see if I can get it to, oops, I don't like it. Well, I guess I can make it. It looks like this. Oh, there we go. And then we have our altitude, which is the height. The altitude is the height of the triangle. All right, so, oh, I didn't label anything. Here's A, here's B, here's C, and there is D. Okay, let's start our proof. Remember, we're always going to start with what we know. So my proof, I'm going to begin with the fact that CD, segment CD, is an altitude of triangle ABC. And that's given. Okay. Now, where can I go from here? Well, I really am just going to use the definition of what an altitude is. And an altitude, by definition, and I'm going to make a little note up here. I should have done this for median, and maybe I will at the bottom. Your altitude is your height drawn perpendicular to a side. So this is really the perpendicular height, the height straight up and down from the bottom of the triangle to the top. Your median was from a vertex and it bisected the opposite side. Doesn't necessarily meet at a 90-degree angle. So make maybe a note off to the side. median is, that's not the best. Vertex, it bisects the opposite side. All right. So that's just a side note because I didn't write it down earlier. This was really like from example one, just to compare. But going back to this problem, we have an altitude here, which is the perpendicular height. So I'm going to say, now that we know that this is an altitude, it's perpendicular. This segment, this entire segment AB is perpendicular to that altitude. So CD is perpendicular to AB. And that's because an altitude of a triangle is perpendicular to the side it's drawn to. So again, sometimes you have to explain a little bit. An altitude of a triangle is perpendicular to the side it's drawn to. That is just the reasoning. Once we get a little bit more comfortable, maybe we might just say definition of an altitude, but I don't think we all know that yet. So that's why we're going to write it out. We're going to be specific. I like to be specific, and you should too. All right, so now that we know that this is a perpendicular line, CD is perpendicular to AB, now I know that that angle, I'm going to highlight it here, this angle, oops, I already used that color, ADC has to be a right angle. So I'm going to say angle ADC is a right angle. You have to build it up. I can't just say this is a right triangle yet. We know they're perpendicular, so now I'm going to say ADC is a right angle, and that's because perpendicular lines form right angles. Maybe I'll say definition of perpendicular. So we know that is a right angle. So now that we know this is a right angle, overall, I can say the entire triangle then, triangle ACD, the original triangle they wanted us to prove was a right triangle. I would say it is. So triangle ADC are I'm gonna go back to the problem. The problem actually said originally ACD. I switched it up in my head. So it's ACD. I'm just gonna use the exact order they did just to keep it specific. Not that it's different if I said ADC, that's the same triangle. It would be a different angle, but it's the same triangle. But ACD is a right triangle. And the reason? It has a right angle. And I'm gonna actually say angle ADC is a right angle within the triangle. So within triangle ACD. So it has a right angle in it, so therefore it is a right triangle. Proven. Did it. Done. All right, so as you can see, these proofs take a little bit of thought, and sometimes you have to make mistakes, and you have to back it up and go back, and that's okay. Sometimes you have to step away and come back. That's okay. So please keep trying and keep practicing, keep going through those OMHS lessons, and I look forward to seeing you in class. Recording.